We now have our second session, which is about data and MRV. And my esteemed colleague, Tom Frankowitz, will be moderating that session. So I hand the mic over to Tom, and you need to speak into the...
Yes. But, all right, thank you, Monica, for the introduction. And absent bios and also my inabilities or inadequacies of pronunciation, I'm going to let my colleagues each give a brief introduction of their name and organization, and then I'll give some introductory remarks and then kick things off, starting with my colleague on my left, Rose. Thank you.
Hello, everyone. I'm Rose Wan. I work at RMI with Tom. I worked at the Digital Innovation Lab at RMI, which is a horizontal function to support programs in developing data and software products. And WasteMap is one of our favorite products that we are supporting. And over to my colleague.
Okay. Hello, good morning and good day. I'm Chandra CID, call me Chandra. I'm from Indonesia, from University Bandung Institute of Technology. So I will talk on the municipal wastewater sector in Indonesia.
Hello, I'm Tia Scarpelli. I'm the waste sector lead at Carbon Mapper, really trying to provide a remote sensing data perspective here.
Hello, I'm Dr. Nupur Bahadur from the Energy and Resources Institute, New Delhi, and we work in the area of wastewater treatment technologies, GHG estimations, mitigation strategies, policy, and advocacy. Thank you.
Excellent, thank you. So I just wanted to provide a little bit of context for MRV, and the reason for that is I think we all talk about MRV in different ways. And I think many of us are perhaps experts on MRV, but also maybe forget that when we're talking about MRV, we're actually maybe talking about different things. So I wanted to provide a little bit of context for that. First off, MRV doesn't always mean measurement, reporting, and verification. Sometimes it means monitoring. So, you know, again, there's a difference in taxonomy here, but generally speaking, there are a couple primary uses of it. There is the use of MRV for compliance, carbon accounting, emissions transparency. The compliance segment, is generally speaking for regulatory or enforcement actions, and there could be a couple audiences for that. It could be at the national and subnational level for in-country regulations at a state and local level. It could also be to meet international climate commitments, most obvious being through the UNFCCC and commitments that countries make for their NDCs. The other category for carbon accounting or emissions transparency, I think is where you'll see probably the widest variation. This could include something much more specific like a certified emission reduction, but it could also be to help meet corporate goals, right? More a mixed of qualitative and quantitative objectives. It could also be for something, kind of in a newer area, somewhere in between a CER and a climate goal to meet corporate-wide goals for energy reduction. So, for example, for sustainable aviation fuel, a lot of airlines have made commitments to offset a certain amount of their emissions, and so those emissions can be documented in something like a book and claim. And also, just more generally speaking, to mobilize finance. WRI actually put out a great thought piece probably about 10 years ago now called their MRV 101. I don't think the terminology really got uptaken, but I think it's worth visiting because it kind of gives the different categories of MRV, and it's a good primer on the topic. And I'll just give an example here. I'm definitely not going to cover all the elements of this slide, but some of you may be familiar with the Low Methane Initiative that was launched at the Conference of Parties. Seems like a long time ago, but just a few months ago now. The Lowering Organic Waste Methane Initiative. This was kind of a sub-initiative under the Global Methane Pledge, where a group of jurisdictions at the national or subnational level could commit to reducing emissions, methane emissions from the waste sector by committing to certain goals. And that would unlock data assistance, technical assistance, finance assistance. That common thread is MRV. And so myself and my colleague Rose, for example, are helping out on the data solutions team, this left pillar in the yellow, that are helping develop some of these principles for data collection, data use, and then also working with the finance team so that we have a common playbook that we're all working off of to unlock finance and to document emission reductions. And that is the value of MRV that my colleagues will be speaking about today. And next we'll have Rose speak a little bit about the waste methane assessment platform.
Thank you, Tom. Yes, thank you. So first of all, waste map, and I don't know whether you've noticed, MAP is an acronym. It stands for Methane Assessment Platform. And so first of all, why waste map? The reason we develop waste map is to resolve the situation where decision makers lack key data to make informed decisions. For example, international civil society or the national government might not have the full knowledge of the whereabouts of the dump sites and landfills. They might not know which landfills are emitting the most methane, so the magnitude of emissions are uncertain. They might not know what are the actionable measures to deploy for specific types of landfills or dump sites, and there's a lack of estimate and measure emissions, lack of ability to estimate and measure emissions reductions. For waste map, we adopted a two-pronged approach. If you look at the left-hand side, this is our first prong, which is the platform itself, the waste map platform itself. The platform contains several layers of jurisdictional methane data, including country layer, city layer, and site layer data globally. And a unique feature of the waste map is the decision support tools, which is a scenario planning tool for decision makers to see what they can do differently to manage their methane problem. We also can, on the platform, we also host a series of strategic playbooks for waste methane mitigation and case studies. On the right-hand side, you can see the second prong, which is the country deep dives. We are providing on-the-ground support to subnational and national governments to help them find a pathway for waste management improvement to improve not just methane emission reduction, but also public health. And in addition to that, we're creating and convening a network of waste experts and peer-to-peer exchange to allow knowledge sharing, for example, from South to South knowledge exchange. So in following up, we will first show an intro video for Waste Map, the platform itself. I will discuss briefly our country deep dive work, our second prong, and then I will talk about why Waste Map can be a key platform for the MRV work.
When we talk about the drivers of climate change, carbon dioxide, or CO2, is usually top of the list. But there's another superheating gas that warms our planet 80 times faster than CO2 in the near term. The culprit? Methane. Luckily, methane moves out of our atmosphere a lot quicker than CO2. So if we cut these emissions now, we can have a huge impact on limiting global temperature rises. One place to start is the waste sector. It's the third largest source of global human-related methane emissions. The good news is, solutions are available today. From minimizing food waste to better gas collection at landfills and other waste collection sites, reducing methane from solid waste is within our reach. To tackle this methane challenge, RMI, in partnership with Clean Air Task Force and with support from the Global Methane Hub and Google.org, developed the Waste Methane Assessment Platform, or Waste Map, an online platform that brings together the data on waste methane emission and provides tools to help waste sector stakeholders make decisions. Each page of the Waste Map site offers unique functionality with insights about waste sector methane and strategies to reduce these emissions. The world map ranks the emissions intensity of waste sector methane in a specific area. Click on a country to view its emissions time series, list of solid waste disposal sites currently available, and global emissions ranking. Within each country, each navy dot represents methane emissions from a city modeled by RMI, and each brown dot represents a cluster of solid waste disposal sites that you can further explore. You can click to view site statistics, such as methane emission rate and waste in place. Some sites offer plume view and plume emission rates. One unique feature of WasteMap is our Decision Support Tool, or DST, that allows decision makers to compare the methane mitigation potential of different waste management practices. Select the country, city, and scenario start year to view baseline data, including existing waste diversion practices. Using the city of Lagos in Nigeria as an example, on the right, you can see the baseline emissions shaded in navy. Let's increase composting. Now you see a decline in methane emissions. To model something else, click the Reset button and the sliders will return to baseline position. Mitigating waste sector methane emissions also requires action-focused strategies, custom-tailored for specific communities and regions. The Resources page features our work to date, including methane mitigation strategy playbooks, technical analysis memos, and more. RMI is partnering with stakeholders in the waste sector to expand the database underlining WasteMap and put the tool into action. Working together, we can reduce methane emissions from the waste sector, a critical step to limiting near-term warming and an essential part of avoiding a climate catastrophe. Contact us to learn more about how you can get involved.
So over the last year, we've launched a series of strategic playbooks, and one of which is a global playbook. In the global playbook, we've defined the waste management archetypes based on the current waste management practices of the cities. So basically, we defined 4 different archetypes. And the first archetype is a build the basics, which means this city might not have much waste collection, and there's lots of open dump and open burning. And the second archetype is build the basics plus, or BTB plus, where the city has already started collecting waste, and some of the waste goes to the sanitary landfill, but a lot of them still goes to open dump sites and active, open burning. And the third archetype is move up the hierarchy, where there is some source separation, like recycling, and most of the waste may be already going to landfills, but there is lack of monitoring of methane emissions, and there's lack of methane capturing system available. And the final and best archetype is a closed circle, or CTC, where there is, very, it's almost 100% collection rate and very good source separation, a lot of recycling, and lots of diversion. And this archetype relies the least on landfill because most of their useful resources are already being recycled and it's like already reaching the circular economy. In the playbook, we assess these the management challenges across these different archetypes and provide solutions for decision makers at every level to improve their waste management practice and reduce methane emission. So the key goal of our country engagement work with the application of the Waste Map decision support tool is to help the jurisdictions, including the cities and national government, to move up their waste hierarchy from the BTB to BTB plus to MUH and all the way to CTC. So coming to our topic, MRV, how WasteMap can play a role in MRV. So first, we will discuss at the city level how we can provide a decision support capability. So if you remember in the video, we demoed about a decision support tool, which is composed of lots of toggles on the left-hand side and a chart on the right-hand side. So when you first go to the DST and pick a city, for example, United States and Washington, D.C., you can see a dark blue chart on the right, which is what we simulated the emissions, the current baseline emissions for Washington, D.C. over time. And the inputs for this simulation includes waste composition, per capita waste generation rate, precipitation, current waste management practice, such as how much goes to different diversion channels like composting, recycling, anaerobic digestion, incineration, etc. It will also needs key inputs such as how much of the waste goes to landfill versus dump sites, whether there's any existing landfill gas capturing. Underneath this, baseline estimation tool is the SWEET EPA solid waste emissions estimate tool, or SWEET model. We converted the SWEET model, which is currently Excel model, into a Python model, so we can kind of host it at the back end of this decision support tool. So the left-hand side toggles are all those diversion scenarios. So now if we increase the composting percentage from the baseline you've seen about like 7 to 8% to 23%, and increase, say, the landfill gas capturing from 0% to 54%, what will the emission reduction be achieved with this kind of combination of policy or projects? So on the right-hand side, you can see a light blue wedge, which is exactly the reduction that we can see with this scenario combination. So the power of DST is for decision makers to see the what-if scenarios without spending the money actually implementing, the projects themselves. They can simulate and see what would be the best combination of scenarios to reach the maximum reduction, and within the given budget. And it is also best suited for simulating those upstream interventions like diversion, because without a mechanistic physical tool, it is hard to know what would be the emission reduction if there is, anaerobic digestion or, source separation. So regarding MRV, we can use, Waste Maps DST as a tool to hold data as well. Over time, if the city, have on-the-ground monitoring data and, satellite drone data, we can measurement data against this trajectory as well to see whether the previous selected scenario, like for example, if they decided they want to go for composting and they adopted 20%, 23% composting scenario, we can compare this actual monitoring data with what is projected at the beginning to see whether the project has achieved the expected emission reduction. And finally, WasteMap has a site level data as well, where we are hosting the satellite data and also modeled emissions data for the sites. And we will be developing site level mitigation scenarios using a site level DST as well for users. What's next for WasteMap? We're planning to engage with more users, encourage other, waste sector partners to contribute data to the site. We're planning to leverage AI to expand sites covered and waste data included. We are planning to expand country engagement with partners at Clean Air Task Force. And we want to expand the functionality of the DST for expanded capacities, including site level DST. And finally, we want to customize functionality to support initiatives under the Global Methane Pledge. Please stay connected and please sign up at this address. And also you can scan this QR code to visit the site site address. I think Emma might have already put the URL links in the Zoom chat. Thank you.
Thank you, Dr. Wall. Sorry. Next will be moving on to Dr. Chandra from the Indonesia Bandung Institute of Technology, who will be presenting on his research on emissions from the wastewater sector in Indonesia. Chandra?
Thank you, Tom. In the next 10 minutes, I will share with you about the greenhouse gas emission from the municipal wastewater sector in Indonesia. I think I will move briefly regarding, but basically is regarding the domestic or municipal wastewater treatment overview, and then how we try also to measure in a small pilot scale, and also some study has been done so far, and also what is the challenges of the measuring the GHG emission from the domestic or municipal wastewater. So that's you might be aware that Indonesia is islands country with a population around 270 something million, 270 millions people now, and mostly we in the calculation of the GHG emission is using the tier 1. So that is the we aware is very simple one. And when we calculating and reporting by the government, it is using the that one is cross ministry and also subnational governments. The challenges is in the municipal wastewater management is limited in the infrastructure, and of course most of them is widespread use of the septic tank. So then some of them is untreated wastewater remain a significant one. So that one is the challenges to knowing exactly what is how much the greenhouse gas emission from the municipal wastewater. So that is the inventory is it is still, I think, very limited, and that one is very crucial for achieving Indonesian emission reduction targets, and that's so that one is based on the GHG emission of Indonesia from the waste sectors. So that one is all using the tier 1. So that is increasing year by year. Either it is from the domestic solid waste, and also from the domestic wastewater, industrial wastewater, and also the industrial solid waste. So the main fraction, of course, from the domestic solid waste and then domestic wastewater, and also from the industries. So that is the target has been set up by the Ministry of Environment and Forestry. It's very the target is achieving 2060 will be the zero waste and zero emission. That one is a very big task, because in the last 10 years, almost doubling the emission, and within 30 years we have come to zero. That is a very quite challenging part. So that one is the overview of the Indonesian municipal wastewater, and 70 best. That one is based on the data. 73% is still using the individual septic tank on-site system. Only around 1% centralized and decentralized system. So we call it a combination with the centralized and then with the decentralized or DEWATS, or we call it the communal system, is around 1%. So it means that around 20 something percentage is still the discharge directly to the river. So that But of course, the government having the data, so that one is the what is the claim by the government that one is the greenhouse gas emission from domestic wastewater sector. So they're increasing, but that based on the data of population. So that one we have to be aware that there is a gap between these data reported by the government and the real one. So no one know what is the real one. At the moment, we do not know. So it's why that we try to measure the greenhouse gases from the decentralized wastewater treatment plant. Of course, it is quite challenging because of the treatment system process is very variable, and also the data is we don't have get data, even it is built by the public works or build the NGOs, we have a difficulty to get access to the data, and also the others like it might be modeling. If you are using the modeling and so on, we still there a lot of uncertainties. So that is the challenging. And then one of the case study, but I will just quick. The case study is about the a pilot plan. It is for the communal system, DEWAT system, in one location in Bandung. So that one is in my city. So that one is built by the Minister of Public Works. I think this in the last 10 years, the Ministry of Public Works, I think, bill, I think, around more than 200 or more, and then the others billed by the NGOs and also billed by the Ministry of Environment. So that one is the way they try to reduce the load, the organic load to the rivers. So that one is the using the anaerobic filter. Basically, it is the anaerobic filter, and then for some we try to collect data, but it seemed to be no data on the how to measure the flow rate. And then also we collect the data BOD, COD, and also the others parameter for along the input and outlet and inlet and outlet of the WWTP, and then we try to calculate the greenhouse gases. But that one is the way we sampling methodology. I think so. I will skip, but that one is one thing we have to understand about the BOD generations. So the BOD generation is because of we don't have we cannot get access to or we cannot measure the flow rate, the water flow rate goes into that one is very difficult. But we have the data, the BOD generation for in the dry season is around 30 to 43 gram BOD per person per day. That time is rather close with the IPCC 2006 is around 40 gram per person per day. So that one is the other study is in the septic tanks. So that one is around 10 years ago, and there's deeper studies about the septic tank. But that one is we found out that for the BOD generation is relatively similar with the IPCC 2000 around in the kilogram BOD per capita per year is 17, and then IPCC is around 14. But when we measure to the emission factor from the septic tank, it's much higher. So that one in that study is a 0.6 kilogram methane and kilogram per kilogram BOD. So that one in the IPCC 2006 septic tank should be multiplied by 0.5 is 0.3. So based on the IPCC and the finding of the study on the septic tank. So the greenhouse gases from septic tank double, then reported by IPCC. So that one is quite challenging. One is in the biodegeneration, and the second one is about the emission factor of methane, and also, of course, the other one is from N2O. So that one also we not yet calculated currently. So that is the finding. Basically, the finding is from the studies is we don't have yet the right data or the correct data how to use the emission factor gas greenhouse gases from the municipal wastewater, especially from the septic tank and also from the communal system. And I think although the government is the I think I move. Sorry, just I will like. Yeah. Sorry. Yeah. Okay. Yeah. I think so. I think although the government have a decree that have to reporting about the data and using the IPCC 2009. However, we still have difficulties in the firm about the infant. And also even they have developed the web-based system information system, but I think the data we are not been a proper one. So that is it is one of we have to take the message, and we have to conduct this study more on the emission factor, and then BOD generation per capita, and then also we would like to have the develop the capacity building, because all the calculations should be done by the local government. So we have to have the guideline, disseminate the how to calculate the greenhouse gas emission through the capacity building. So I think that I would like to conclude that the other thing is in the future we have to data collection and monitoring and technology and so on and so on. So I think I would like to conclude, and would like to thank to the GMI and also UHPA and also other colleges in collecting this data. Thank you very much.
Thank you, Dr. Chandra. And next, we'll have my colleague, Dr. Tia Scarpelli from Carbon Mapper, speak about their work on MRV and data collection in the waste sector. Tia?
Thank you, Tom. So yeah, I'm Tia Scarpelli, waste sector lead at Carbon Mapper. I'm going to be talking today about using remote sensing to drive mitigation action in the waste sector. Noting that I'm the waste sector person, we also do a lot of work in other sectors. So some of what you hear today about remote sensing can apply and go across different sectors. I'm going to focus on solid waste. For a little bit of background on what Carbon Mapper is, we're a nonprofit organization that tries to deliver actionable and transparent methane and CO2 emissions data. This is really focused on facility scale emissions data, and I'll talk a little bit more about that in a sec. We lead a public-private partnership that is developing and deploying emissions detecting satellites. When we plan to launch first satellite in 2024, so this year. We have a longer term goal to scale up to a constellation of satellites that can track 90% of high emitting methane and CO2 point sources, and I'll define point source in a second, globally on a daily basis. And all the CO2 and methane data that we collect is made publicly available on our data portal. And I have some partners shown on the slide, and just kind of a preview of what the satellite data looks like for methane. So a little bit of background on remote sensing instruments and what we consider point sources. So on your left, I'm showing just a diagram generally of methane detecting satellites It's kind of a confusing space because there are a lot of satellites. You might have heard about a few already here at the Global Methane Forum. There are generally two categories, and I'm very much generalizing here. On the top are what we consider area flux mapping satellites. So these satellites are looking generally at regional to global methane in the atmosphere. They're really good at getting like national emissions. We can use mathematical tools to backtrack to emissions data. But their focus is really generally more regional. And then in the middle plot, I'm showing also an example of what the data looks like. So this is showing a methane hotspot over an urban area in Buenos Aires from the Trapomie satellite. Whereas I'm not going to really focus on this data today. I'm going to talk more about what's on the bottom of the left figure, which are point source imaging satellites. So these are really looking at facility scale, what we call a methane plume. So it's a methane concentration above the general background of methane that's related back to a specific source at a localized area on the ground, like a landfill, for example. So I'm showing this in the far image, where it's just an example of, this is from the EMIT NASA satellite, where it's a methane plume coming off of a landfill. So the landfill boundary is the white kind of rectangle shape. And it's really specific to this localized area on the ground, which is what we call, I'll refer to as a point source. And so it's just important to kind of make that distinction that not all methane detecting satellites are the same. They have different use cases, and especially when it comes to how they're used for mitigation. I'll also be talking a bit about aircraft data. So the instrument that we use for the satellites can also be flown on aircraft. And so Carbon Mapper also has done many aircraft campaigns, mostly focused in North and South America to date. And then in the middle image, I'm actually showing it's the same landfill, still showing a methane plume, but this is with aircraft data. And you can kind of see how the satellite data and the aircraft data, same type of instrument, but there is different in terms of the resolution of the data. So why do we care about point sources? The point sources, or these localized and area large methane emissions, can account for a large fraction of regional emissions. And this does vary by sector, but we do see point sources across different economic sectors that have methane emissions, especially in the oil and gas and the waste sectors. More in solid waste than in wastewater. And we've found so far in the US that at landfills where we can compare different types of measurement techniques that do total emissions versus just point source emissions, we found that at a subset of landfills, the point source emissions can dominate total emissions, whereas the total emissions from the landfill are generally the point source emissions. And I'm just listing here, I won't go through all of these, but just different ways that the data can be used in the mitigation process. This can range from, helping an operator on the ground figure out like where is my leak actually located on the ground, to looking at trends in time from a specific facility's emissions. So going back to the waste sector specifically, here I just want to go through kind of what we generally use this data to look at within the waste sector. So this includes on the left, I'm just showing different types of facilities within the value chain where we've seen emissions in the past. This can be at dump sites and landfills. It can also be at if there is beneficial use gas facilities at the landfill. We can also see if they have flare stacks, for example, and there's some sort of operational issue, and so they have methane venting from the flare stacks. We can also see that. We've seen methane plumes from compost facilities and organic digesters. Usually this is not that common. It's usually something is going wrong. Maybe they're not aerating their compost properly at the facility or something like that. When we think actually at the facility, especially here I'm showing a diagram of a landfill, there are different processes on the ground that can actually lead to the generation of these point source emissions. This can range from, the gas infrastructure that's there, if they have a flare, or if there's the wells, if there's, maybe the well is flooded and so it's leading to methane release from the well. Also where we're actually actively filling the landfill at the work phase. This can also be a source of large emissions. So zooming out again and just thinking about generally point sources that we can detect with satellites. Here I'm showing, this is if you go to our data portal where all of our data is public, this is what you would see. So this is showing just regional totals in the purple circles of how many point sources we've detected in a given region. This is a combination of airborne and satellite data. For now, the global data is coming from the NASA EMIT satellite, but when we launch our own satellite this year, the data will also be going onto this data portal, and it will populate some of those regions where right now we don't control where the NASA EMIT satellite looks. So you can see in the purple, kind of the more diffuse purple boxes regions is showing where the satellite has observed. And so not everywhere the satellite observes, we don't see point sources everywhere. But you can see as well that, this satellite data that we have here right now is regionally biased, where it doesn't look, because it was designed as a dust mission, not a methane mission. So it tends to look at dusty areas. So that's why that explains the spatial bias. And on the bottom, I'm just showing kind of aggregate emissions by sector for the view that we're looking at. And so the yellow is oil and gas, and then brown is the second biggest contributor, and that's the waste sector. And if we zoom in on a particular region, we can see, so the purple boxes here are showing where the satellite or where the aircraft have observed. So I'm zooming in over Santiago, where we've done both airborne campaigns and we have satellite data. And then the purple circles are showing the individual methane sources. In Santiago, most of the point sources that we've seen have been at landfills. And then on the far side, I'm showing the actual emissions per facility. And you can actually go and look at the actual methane plume images for different times that we've flown the site. And then we also have the aggregate statistics for Santiago. So you can zoom in on a particular urban area and look at, what are the emissions by sector that we've seen with the instruments. I'm also then showing here, what have we learned in the waste sector from, this data so far? So we've done a lot of airborne campaigns in the US. We've seen over 200 landfills emitting methane in the US. And generally we find that these emissions are persistent over time. That means as we revisit them on different days or in different years, we see that the ones that we see emitting generally are still emitting when we revisit them. And so far, what we've seen with the satellite data globally is that this is, this is true in different countries across different regions. That, generally the sites that we see having large emissions, whether it's a dump site or a landfill, as we revisit and look at them again, they still have these large point sources, though the magnitude of emissions does vary day to day. And here I'm just showing an example zoomed in. So the image that it's going through is these are methane plumes coming from a site just outside of Alexandria in Egypt. And it's showing, you can see the wind kind of move the methane plume around in different directions on different days. But then we also have, you can see the temporal emissions day to day and how emissions are changing as we revisit the site over different months. And then just to kind of bring this together by country, noting that we have not looked evenly in different countries with the satellite data. So just keep that in mind when looking at these country totals. But this is just showing the number of point sources in the waste sector that we've detected by country. The highest is the US because we've collected more data there. And then averaging the emissions across the facilities on the far in the purple bars. Generally, we see that actually emissions are similar at these large sites in different countries. Generally around 1,000 kilograms of methane per hour. Remembering that all of these different instruments have different detection limits, so they can only see sources that are so small. So that is going to affect the emissions that we see in which facilities where we see emissions. So just then thinking about how does this data go to supporting mitigation can range from planning. So thinking about, this is over Sao Paulo, looking at different emissions from different facilities. How do we prioritize mitigation? Which ones do we want to attack first? If there are larger emissions from a certain site, maybe we want to go and invest in mitigation at that site first, just to get the low-hanging fruit. Then in the middle, thinking about monitoring, how using the data to identify, what is the source at the facility, if we go and do mitigation, do we actually see a change in emissions? So the data can be used to verify that, yes, emissions were reduced. This is showing an example in California landfill where we worked with the operator to do that. And then the far one is just showing, looking at when we think of verifying emission inventories, if we compare the observational data to the emission inventory or the model, what can we learn? So this is showing an example in the US where we've looked at inventories and we see that the facility emission inventories are generally not agreeing with observations. And so why is that? Are there certain sources that are misrepresented? And just noting as well that we have global partners that help us, map the data and the science to actual action on the ground. This includes the Low Methane Project and Waste Map, which you've heard about already today. Thank you.
Thanks so much, Dr. Scapelli. And I think very notable on an MRV panel, everyone is staying on time, which I really appreciate. And with that next, the last speaker is Dr. Nupar Baduhar with the Energy and Resources Institute, or TERI, from India. And she's going to be speaking about their research on wastewater as well. Dr. Bahudar?
Yeah. So, good morning to one and all. And I'm grateful to GMI, US EPA, UNEC for having me here and supporting this. And when I am looking to the speakers here, so I would say that a lot has been done across the globe and much more has to be done in our area, in our country. So we are just beginning with it. So we have a few studies. And today, in this session of importance of data collection and MRV, when we say it is particularly important. So I'm going to talk about the GHG emissions for the domestic wastewater sector in India. And basically, you all might be aware that in India, a lot of emphasis is going on the wastewater treatment. A lot of national missions have come forth and various cleaning efforts are going on in the country. And also we have started working majorly on the GHG emissions and mitigation strategies. For coal, agriculture, we are bang, and energy, three sectors we are bang on there. But definitely for the waste sector, we haven't done much, I would say. So we have started working in this sector as well. And particularly what the gap, what we face here is the estimates which are provided by the Global Greenhouse Gas Program of India and those submitted to the IPCC panel by the Ministry of Environment and Forest. So there is a disparity in the data. So we have to have a standard data in the country. So this is something where we are beginning from. And we have to assess the government's methodology, which is required. And to resolve these disparities, it's imperative to engage all stakeholders and extensive discussion. So I'm really grateful to be here and learning a lot. Also, when we see the global anthropogenic methane emissions by source, we see for the waste water sector, it's 6.1. And when we see India, so it's majorly, it's around 7% of the global estimates. This background, we backed actually a project from US EPA, and together with Tetra Tech and TERI, we undertook a study on GHG gas emission inventorization in wastewater sector in India. So this is one of the few studies which have been undertaken recently, and our objectives were very clear how to inventorize. We have to look at the decentralized and the centralized wastewater treatments, and we have to analyze the existing reporting methodologies, which was a very crucial part of this project. And we have to offer recommendations to the GHG emissions. So I'm here to disseminate the findings of this successful project undertaken with Tetra Tech and funded by US EPA. So now coming to the point, when we see the wastewater generation scenario in India, it's 72,368 MLD, which is generated sewage, which is, we are talking of domestic sewage here. So this is which is generated. And when we see finally the treated, it is merely 20 to 30%, which is, and only 70%, which is meeting the safe discharge norms, which means we have huge responsibility still with us to treat wastewater and see if we can mitigate the GHG emissions. So this is also on the capacity we have to enhance on the wastewater treatment. So when we see 10 states, we are 28 states in the country and 8 union territories. So when we see 10 top states in the country, you see here in the second column the percentage. So these top 10 states constitute 72% of the wastewater in the country, and Maharashtra tops the list. And likewise, all states have been arranged. And on the right, you see the sewage treatment capacity that is also there for each of these respective states. So, coming forward now, this is where we have two agencies, the Central Pollution Control Board under Ministry of Environment and Forest, and then we have National Mission for Clean Ganga under Ministry of Jal Shakti. So having two different ministries monitoring the inventorization of the STPs, and they both have different parameters. So one assumes 185 LPCD of water supply every day, and the other sees 135 LPCD. So what we are right now government of India is trying to do is have a common platform. First, inventorization has to be with one ministry or a centralized ministry so that disparity is not there. So this is what we are beginning with. As a result, when we see the two ministries, the data, what we see is the difference in the data, what we see here. So with Delhi being the capital, has the least disparity in the data, and Maharashtra as largest in the sector doesn't have any disparity, much disparity. So what we conclude from this is that the state which has highest contribution, which is contributing highest in the sewage generation, has the highest capacity of treatment as well. And Delhi, which is also a state, is it generates least 6% of the total national estimates and has the highest treatment capacities, 87%. So, and for example, a state like West Bengal has least treatment capacity. So this kind of data is coming across the country. Also, we are looking at different treatment technologies which are contributing more to the treatment and also to the GHG gas emissions in the later part. Also, we have see the DWATs, the status of DWATs. So until recently, DWATs are not encouraged, but very recently, with various national programs, government is massively encouraging the DWATs or the decentralized wastewater treatment systems. Now coming to the GHG estimations from these wastewater sector, this wastewater. So what we see here, we consider these as direct and indirect emissions. This is a very well-known fact which we are considering. And in this study, what we have approached, the methodology has been, we have the GHG platform from India has been covered. Platform published a report on 2022 on national GHG estimates, which were there, and a period from 2005 to 2018 has been covered in this study. And also GHGPI estimates were compared with the India's biannual updated reports, which were submitted to UNFCCC. So this is the conclusion. What you see in this is the source category. And when we see from 2005 to 2018, of course, in all categories, there is enhancement in the GHG emissions. And 4D1, when we see the domestic wastewater treatment and discharge, there is 45% rise in this sector. Now coming to the sewage generation versus GHG emission. So for the same 10 states, on the left, we have sewage generation capacities or the percentages, and on the right column, we have the GHG emissions for these 10 states. So what we conclude from this is that the Maharashtra and Uttar Pradesh, which are the top states. So Uttar Pradesh has the highest GHG gas emission rates, and it is the largest state as well. And Delhi, as I said, is lowest in sewage generation, but having 87% treatment capacity is not there in the GHG emissions, whereas Bihar and West Bengal, which are less developed states, they are in the GHG emissions. Here, what we see is the comparison of GHGPI estimates with that of the IPCC reports, which are submitted by the ministry. So what we see here is initially there was huge gap, but now that gap is being bridged, And now with this is the data until 2016 or 18 we have considered, but in recent time for last 4 years, the data has seen significant improvement and there is not much disparities now. So key takeaways, if we have to see from the study, is that domestic wastewater treatment discharge emerged as a primary contributor, constituting 55 to 56% of the total GHG emissions in the country in the waste sector. And top 10 states. So the bottom line is the states which are treating their sewage well with good capacities, they are not in the GHG emission list, which means better treatment leads to less GHG emissions. Likewise, emissions from domestic wastewater sector amounted to 43.82 million tons of carbon dioxide equivalent, has risen to 63.76 million tons of CO2 equivalent. So this is something which we are there working for, and the biennial reports of the Government of India are expected to provide more clarifications on the data used for the estimations. So this is something where we have to work on the methodologies, and we have to come up with the way forward is four major things here from this platform. I really look forward to all the partners, and here we can look forward to first have a baseline data needed to be strengthened for sewage generation, treatment capacities, and treated water for each state along with the type of treatment technology employed. So this is what is most essentially required. And also one common platform, one ministry should be responsible for this data. Second way forward is inventorization of the STPs and again, a common platform for the data. Third is the Ministry of Environment and Forest and Climate Change, Government of India need to release GHG emission data for Tier 1 for all states for the period 2018 to 2022. So this will bring much more clarity in the data. And last but not the least, we have to develop the tier 2 and tier 3 methodology with on-field calculations, which is crucial for deriving an accurate estimations of India's specific methane emissions in the domestic wastewater sector. So here, as you see, I invite all the partners, and just today itself, I received the call right here from the Department of Science and Technology, Government of India. They have launched a methane platform, and they would like to collaborate with GMI. So it's a great initiative. Just today, I got calls from 2 ministries, and I really look forward to GMI working with Government of India and Department of Science and Technology. Thank you so much. Thanks for giving me this chance.
Dr. Bahudar, that's excellent news, and thank you for keeping us on time. And we would love to work with the Department of Science and Technology as well. And of course, we would love to have your data in the waste map. So Thank you, everyone on the panel, for excellent presentations, for keeping us on time. And in that spirit, we're not going to have questions and answers, but I prepared some really excellent questions. So maybe I will just ask one that people could contemplate during the coffee break. So I'm curious, we hear so much about the advance of satellites as a game changer. Also, things that aren't talked about that much are things kind of nearer the ground, like drones and fixed monitors and towers for on-site measurement of fugitive emissions. And one thing that I'm curious about is how those various components interface, and if we expect that technology will replace tried and true data collection, modeling, things like that, or work to eventually make those better so they work in harmony. And so maybe that's something folks could think about and talk about during the coffee break right outside. Thank you, everyone.
Thank you so much, Tom, and the panelists. We do have a 10-minute coffee break just outside. I recognize that the chatting part and the questions is the really important part of this. We do at the end of the day have a session that's an hour and 10 minutes, there's no agenda. It's about discussion. So I really hope that we can have a discussion on different topics during that time. So please stay for that. So enjoy the coffee, come back in 10 minutes, and I will round everyone up. Thank you. And thank you, Tom.